Hi, my name's Daniel and I'm here today to talk to you about geophysics. Geophysics is physics of our Earth. Geo means Earth. So I have a question for you. Why does our Earth have a magnetic field? Acting from the poles, we have a magnetic field. Why? Well, one theory is that the rocks in the Earth are magnetic. There's plenty of iron in those rocks, so maybe they're magnets. Well, the problem with that is that inside the Earth, deep inside the Earth, it is very hot. And that heat will destroy a magnet. Well, let me show you. Here is a magnet. Pick up this steel disc, and the disc is magnetic, so no problem. And doesn't matter which side I use. But if I heat the magnet, give it lots of nice heat, this is like what would happen to a magnet inside our Earth. It would get very, very hot. And now, it is no longer a magnet. Here is my steel disc. And it's not a magnet. So the magnetism would be destroyed if it were simply a case that the rocks were magnetic. A very famous scientist who gave this a lot of thought was a man named Sir Isaac Newton. And Sir Isaac Newton knew a lot about gravity. So here's a picture of Isaac Newton and me. So Isaac Newton had deduced that gravity was 9.8 meters per second squared on Earth. And this was an accurate value that he knew was directly proportional to mass. He had deduced that mass was responsible for causing gravitational field strength. So G was proportional to mass. This meant that he could do an experiment and he could test any calculation for mass against this value of G that he knew to be accurate. And mass can be calculated by multiplying density and volume together. And that means that he only has to find these two things in order to be able to calculate the mass of the Earth. And then he can test how accurate it is against G. Volume was a mathematical solution because he could approximate the volume of the Earth to that of a sphere and use the formula 4/3 pi r cubed. This meant that Newton needed to find the radius of the Earth. Unfortunately for Newton, this had already been done. A Greek over 2,000 years ago had come up with a remarkably accurate estimate for the radius of the Earth. His name was Eratosthenes, and he was studying in Alexandria. He also travelled to Aswan, and with the curvature of the Earth, we put Aswan here. Aswan was a very famous place because it had a well, which is a deep pit, which we can think of like a big cylinder, which has water at the bottom. And the reason it was famous was because at 12 o'clock, noon each day, the sunshine was directly overhead, and that meant that the base of the well did not have any shadow. The sun was directly overhead. And Eratosthenes decided that he would test this out in Alexandria, and he put a big pole in the ground. Big pole, like a big stick. And at the very same time, 12 o'clock noon, a shadow was cast, which meant the sun was not overhead, it was over here somewhere. And indeed, if we get a shadow form, we're able to calculate with some simple geometry the angle. Now, the angle that Eratosthenes managed to calculate was approximately 7.2 degrees. And if we compare that to the time it takes for the Earth to rotate once, that would be 360 degrees, then the position from Alexandria to Aswan is the amount of distance relative to the Earth's circumference that would be equal to this fraction. So this was approximately 800 kilometers, and therefore the Earth's circumference could be estimated, and the Earth's circumference is equal to pi times d, and of course that's pi times 2 lots of the radius. So we now have the radius, and we've had the radius of the Earth to within about 2% of the actual value, approximately 2,000 years, or more in fact. It was BC. And that gave Newton the volume, and it was a volume that was known to be within about 2% of the actual value, so he could rely on this to be accurate. That just meant he now had to consider the density. Okay, so Newton was looking for a density value. And what better way than to consider what the Earth is made of? And if you consider the rocks that you will find in your garden or in the street, you'll find things like this. You'll find sandstone. So this is made out of sand. This particular one is quite a red sand, so it has a lot of iron in it. And you can see there are some lines in it where the sand has laid down over many years and compacted into this rock. You will also find a lot of limestone. Limestone is typically quite white, and that's because limestone is effectively chalk. This is the purest form of limestone. It comes in many forms with other bits and pieces in the rock. Lots of limestone, lots of sandstone. You'll also find things like this. This is a shale, and shale is basically mudstone that's been compacted and pressed down, many years of pressure, turning it into a rock. So this is a rock, but it is made out of mud, mainly. Sand, lime, and mud. Now, the average density of those sort of rocks that form right at the top of our crustal surface of the Earth is about 2.5 grams per centimetre cubed. Newton, though, knew that the crust contained other rocks that were a bit deeper, and they were probably a bit heavier and a bit denser. And indeed, you can get some rocks like this, which are very hard. That will hurt me if I hit it too hard. This is a very coarse granite. It's a special kind of granite called a pegmatite, and you can see in there really big crystals that have formed, and this is an igneous type of rock that forms quite deep in the crust. So this has a density of about 3 grams per centimetre cubed. So these 2.5 grams per centimetre cubed, and these are 3. So on average, if we consider the crust of our Earth, we have a density of about 2.8 grams per centimetre cubed. And so Newton used that value and put it into his formula. But guess what? It wasn't enough mass to give him a gravity of 9.8. It was way too small. He knew the volume was okay, so the density had to be too small. Ah, said Newton, I wonder if even deeper, even below the pegmatite, there is another kind of rock. And he's right, there is. Inside the Earth, where we have crust, below that we have mantle. And the mantle, many people think it's red, but actually it's not. We think it's red because we see volcanoes and lava and that's all red and orangey, but that's only at the top where it has melted and it's escaped, and that's why we can see it. If we actually look at the stuff that's buried deep within our mantle, then it's more green. This is the kind of stuff you might find. This is a very greeny kind of rock, and it's packed full of a mineral called olivine. Olivine makes rocks green, and you can see this is also a very tough rock. It's very, very hard, and this is very, very dense. So if we take into account the density of those rocks, which fill up majority of the Earth, then we might go up to a density of 4 grams per centimetre cubed. And that gets Newton a little bit closer, but it's still not enough mass. The Earth has more mass somewhere, and we know what's on the surface, and we know what's just beneath the surface. So the only other place it could be is in the centre. In the centre of the Earth, there is something very, very dense. And Newton was one of the first people to suggest that the Earth had a metal core. And he was right. The Earth does have a metal core. Seismic imaging has since confirmed Newton's hypothesis that the core of the Earth is indeed metal, and is actually very large. Majority of it, about 90%, is iron, with the remaining 10% mostly made up of nickel. It's also very hot in the centre of our Earth, and so when the metal, iron, reaches the temperature of 4,000 degrees centigrade, it changes state. It becomes a liquid. So we actually have a liquid metal core, and that liquid iron sloshing around is effectively a big current, lots of moving electrons or ions. And that on its own would not be sufficient to give us a magnet and a magnetic field for the Earth. So we do have to have an inner core that is solid. So there's a liquid outer core and a solid inner core. Now, why would that be? Because it's still just as hot in the very, very centre, over 4,000 degrees. The surface of the sun is about 5,000 degrees, so it's certainly hot enough to melt all the metal. Most people are aware that temperature can cause a state change. What not everyone realises is that pressure can also cause a state change. If ever you've been ice skating, your blades are putting pressure on the solid ice and turning it to liquid. And that's an example of pressure causing a state change. Rocks actually work in reverse, that if you really, really compress them under very high pressure, they become solid, even at 4,000 degrees. So the very, very centre of the Earth is where the pressure is highest, and that is why that little section can be a solid. And then we have this remarkable situation of a hot liquid outer core sloshing around solid inner core. And this gives us an electromagnet in effect, which gives us a huge magnetic field of the Earth. To summarise, we can use this apple, which is actually a really nice analogy for how the structure of the Earth looks. If I cut it in half directly through the centre, you will see that we have a core, which of course matches the Earth. The inner core is solid, that's where the pips are, solid inner core. We then have a liquid outer core. We then have majority flesh being mantle. And then the very, very thin layer, this is the bit we walk on, the skin of the apple, is like the crust of the Earth. So this is the structure of our Earth in a simplified form. So it is thanks to our liquid outer core and our solid inner core being made of metal that we have a magnetic field. And it was thanks to Newton and his theories that first made it possible to understand why this might be the case. I hope you've enjoyed today's session, and I look forward to possibly seeing some of you in the future, and I wish you all a very nice day. Thank you for watching.